On the morning of December 7, 1941, approximately 10 miles from Oahu's coastline in the Hawaiian Islands, Lieutenant Mochitsuru Hashimoto stood at his post aboard the Imperial Japanese Navy submarine I-24. As the first hints of dawn approached, he prepared for the submarine's torpedo attack on Pearl Harbor, a strike that would soon engulf the harbor in flames. Hours later, the skyline above Battleship Row would be filled with smoke and fire, marking a triumph that Japanese officers initially perceived as unthinkable, a blow against the United States Navy, a force many in Tokyo had deemed invincible. Within the submarine and across the Japanese fleet, confidence was high. Officers believed the assault had inflicted irreparable damage on the American naval presence in the Pacific, and that Japan's technological edge in weaponry would secure its continued maritime dominance. Yet, beneath this sense of victory lay a profound miscalculation. The instruments of Japan's ultimate defeat were quietly assembling within American submarines, untested and underestimated, dismissed by Japanese intelligence as inferior proof, in their eyes, of Western technological superiority. The trajectory of Japan's naval downfall was not dictated by the dramatic carrier engagements that later captured headlines, but by the persistent and often frustrating failures of American torpedoes early in the war. Ironically, these shortcomings would pave the way for the United States' most destructive submarine campaign in history. The misjudgments and technical underestimations that defined this period began well before the attack on Pearl Harbor. On May 13, 1940, an anonymous source whose identity remains secret to this day delivered detailed intelligence on Japan's Type 93 long-lance oxygen torpedo to the U.S. Naval Attaché in Tokyo. The Type 93 represented the zenith of Japanese torpedo design. Its specifications were staggering. It could travel more than 22,000 yards at 48 knots and extend to 33,000 yards at reduced speed, armed with a 1,080-pound high-explosive warhead. It was, by a substantial margin, the most sophisticated torpedo in the world. The informant provided not only diagrams and performance statistics, but also operational guidelines explaining precisely how Japanese destroyers and cruisers would deploy the weapon during night surface engagements. Despite the clarity of this intelligence, the U.S. Office of Naval Intelligence's assessment proved disastrously flawed. After consulting the Bureau of Ordnance for technical evaluation, the report was dismissed outright. The reasoning reflected a broader bias in Western military thought. Japanese engineers were considered incapable of producing technology superior to their Western counterparts. The notion that an Asian power could safely master pure oxygen propulsion seemed implausible. Consequently, the Type 93 torpedo was underestimated, its potential ignored, and the report was archived, largely forgotten. This prejudice was not confined to torpedo technology. In 1940, Admiral Richmond Kelly Turner, later commander of amphibious operations in the Pacific, testified to Congress that Japanese pilots were inherently inferior due to racial traits, claiming deficits in spatial awareness and night vision. Army Air Force assessments in 1941 similarly underestimated Japanese aircraft, labeling the Zero fighter as an obsolete derivative of outdated Western models. These erroneous assumptions would prove costly in the initial months of the Pacific War, as Japanese pilots, flying highly capable aircraft and employing sophisticated tactics, achieved air superiority over locations such as the Philippines, Wake Island, and the Dutch East Indies. The consequences of underestimating the Type 93 torpedo became immediately apparent after Pearl Harbor. During the course of the Pacific Campaign, 7 American cruisers including Quincy, Vincennes, Astoria, Chicago, and Northampton succumbed to these weapons, often from distances previously considered safe. 9 destroyers were sunk in similar fashion. Even the fleet aircraft carrier Hornet, already critically damaged at the Battle of Santa Cruz, was later struck by destroyer-launched long-lance torpedoes. Over 310 American sailors lost their lives directly due to Type 93 attacks. In many engagements, ship crews believed they were operating well outside the torpedo's effective range. Lookouts scanning the horizon saw no immediate threat, and captains navigated based on outdated intelligence that underestimated Japanese capabilities. Yet torpedoes fired from 15 or even 20 miles away struck with devastating accuracy, demonstrating the lethal reach and technological sophistication of the weapon. The first major encounter occurred at the Battle of the Java Sea on February 27, 1942, signaling the start of a series of encounters in which Western assumptions about Japanese naval power would be repeatedly shattered. What had been dismissed as improbable or impossible now reshaped the Pacific conflict. The long-lance torpedo, a technological marvel underestimated by US analysts, would become a decisive factor in Japan's wartime victories and, paradoxically, in its ultimate defeat. The lesson was clear. Strategic misjudgment born of prejudice and disbelief could have consequences as severe as enemy fire. Dutch Rear Admiral Karel Doorman, tasked with commanding an ad hoc Allied fleet, led a mixed contingent of American, British, Dutch, and Australian warships from Surabaya to intercept a Japanese invasion convoy approaching Java. The force under his command was a heterogeneous assembly, including the heavy cruisers Exeter and Houston, the light cruisers Ditta, Java, and Perth, and 9 destroyers drawn from 4 different navies. Differences in operational doctrine, tactics, and language significantly complicated coordination among the ships. Doorman, an experienced and capable officer, faced a daunting challenge. His crews had endured months of relentless retreat. The ships had never exercised together as a cohesive unit, and they were about to confront a Japanese fleet whose sailors had trained together for years under a unified command with well-practiced tactics. The engagement began at approximately 1600 hours when Japanese and Allied forces sighted one another visually, though most of the Allied ships were beyond their effective visual detection range. Japanese heavy cruisers Haguro and Nachi, accompanied by the light cruiser Naka and several destroyers, maneuvered to bring their torpedoes within firing range. At 1,633 hours, Naka launched 4 Type 93 long-lance torpedoes from around 15,000 yards. Over the next several minutes, her escorting destroyers released an additional 27 torpedoes from distances of 13,000 to 15,000 yards. At 1,652 hours, the heavy cruiser Haguro added 8 more torpedoes, astonishingly fired from nearly 22,000 yards over 11 nautical miles. The waters between the opposing fleets became a deadly lattice of torpedoes, running silently just 12 feet below the surface, their oxygen-powered engines leaving no visible wake or bubbles. Allied lookouts and sonar operators, accustomed to the shorter ranges of American and British torpedoes, detected nothing until it was far too late. At 1,713 hours, a Type 93 struck the Dutch destroyer Cortona amidships. The torpedo against the thin hull, breaking the ship in two. Within 2 minutes, Cortona sank, taking nearly her entire crew of 150 with her. Misinterpreting the attack, Allied commanders concluded that submarines had been responsible, unable to fathom torpedo launches from such extreme distances. For the remainder of the day, the Allied ships attempted to evade what they believed were submarine torpedoes, maneuvering erratically and breaking formation, which prevented any coordinated offensive against the Japanese surface units. The battle persisted for 7 hours, with Doorman repeatedly trying to close with the invasion transports. Japanese warships skillfully blocked these attempts. The heavy cruiser Exeter was hit by an 8-inch shell in her boiler room, reducing her speed and forcing her out of formation. Meanwhile, the British destroyer Electra, after a valiant but doomed torpedo attack, was sunk by Japanese gunfire. By nightfall, Doorman's task force had been reduced to 4 cruisers after the American destroyers withdrew due to fuel and ammunition shortages. The Allied ships continued searching for the enemy transports through the night. At 2,325 hours, Japanese cruisers Haguro and Nachi, using radar to track the Allied force, launched another long-range torpedo salvo. Moments later, at 2,332 hours, a Type 93 torpedo struck the light cruiser Java, detonating her magazines and destroying the ship almost instantly, claiming 512 of her 600 crew. Just 6 minutes later, Doorman's flagship Ditta was hit by another long-range torpedo. The explosion triggered catastrophic secondary detonations in her ammunition storage, breaking the vessel in half and killing the admiral along with 345 sailors. By the end of the Battle of the Java Sea, the Allies had lost 2 light cruisers, 3 destroyers, and around 2,300 personnel, while Japanese casualties were minimal, limited to minor damage and a few transport hits from stray torpedoes. The Japanese invasion of Java proceeded unhindered, and the battle revealed the overwhelming lethality of the Type 93 torpedo and the Allied forces' inability to counter it. Despite survivor reports and detailed battle assessments, American intelligence was slow to accept the reality of extreme-range surface-launched torpedo attacks. Analysts concluded that submarines must have been responsible and that Japanese torpedo performance was comparable to Allied weapons. This misjudgment would recur in the Battle of Savo Island on August 9, 1942, resulting in another catastrophic defeat for the U.S. Navy. In the early hours of that night, Japanese floatplanes illuminated the Allied cruiser screen, protecting the Guadalcanal landings with parachute flares. Vice Admiral Genichi Mikawa's force, consisting of 5 heavy cruisers, 2 light cruisers, and a single destroyer, closed a torpedo range under the cover of darkness. Within 32 minutes, the Japanese inflicted devastating losses. The Australian heavy cruiser Canberra was heavily damaged by 2 Type 93 torpedoes and 24 8-inch shells and sank shortly thereafter. American heavy cruisers Quincy, Vincennes, and Astoria were set ablaze and would all sink before dawn. Chicago suffered a torpedo strike that severed her bow but managed to escape. Over 1,000 Allied sailors perished that night, many trapped below decks as their ships burned and disintegrated. These 2 battles underscore not only the remarkable effectiveness of the Type 93 torpedo, but also the tragic consequences of underestimating an enemy's technological and tactical advantages. They remain stark reminders of the dangers of inadequate preparation, poor coordination, and misjudged intelligence assessments in naval warfare. American sailors returning from engagements during the early Pacific campaigns reported torpedo attacks that defied conventional understanding. They described projectiles striking from angles and distances previously thought impossible, leaving no visible wake and detonating in ways that implied the Japanese torpedoes could alter course after launch. Despite these first-hand accounts, U.S. naval intelligence largely dismissed such reports as the product of battlefield confusion, assuming that stressed crews were exaggerating enemy capabilities or rationalizing losses. The prevailing view remained that Japanese torpedoes were broadly comparable to American designs, possibly marginally superior in certain features, but by no means revolutionary. This deliberate underestimation of enemy technology persisted until 1943, when engineers finally examined recovered Type 93 torpedoes from sunken Japanese destroyers and verified the pre-war intelligence assessments. By that point, thousands of Allied sailors had been killed, and numerous ships lost to a weapon American authorities had confidently claimed did not exist. A mirror image of this misjudgment characterized Japanese attitudes toward American naval armaments. Early in the war, Japanese intelligence received reports of American submarine attacks with growing satisfaction and little sense of danger, interpreting repeated failures as evidence of flawed torpedo design and deficient crew training. On December 14, 1941, a week after the attack on Pearl Harbor, the submarine Seawolf, under the command of Lieutenant Commander Frederick Warder, encountered a lone Japanese freighter anchored off southern Mindanao. Warder maneuvered his submarine into an optimal firing position, roughly 3,000 yards from the stationary vessel with no escorts nearby. He launched 8 Mark 14 torpedoes, each a costly product of months of effort, containing over 600 pounds of explosive. 7 of these torpedoes missed entirely, running wide or passing beneath the target. The 8th hit the freighter squarely, but the warhead failed to detonate. The ship's crew, alerted by the impact, managed to get underway, while Seawolf submerged to avoid counterattack, though no depth charges were deployed, as the vessel carried no anti-submarine defenses. Only 10 days later, on December 24, 1941, Commander Tia Jacobs aboard the submarine Sargo engaged a small group of Japanese cargo vessels off the coast of Indochina. The convoy, loosely organized and unescorted, presented ideal conditions for attack: calm seas, clear visibility, and vessels moving at steady speeds. Jacobs executed textbook firing maneuvers, launching 3 torpedoes at each of 4 targets, totaling 12 torpedoes. Yet, in every case, the torpedoes failed, either passing harmlessly beneath the ships, exploding prematurely, or not detonating at all. During the final assault, Sargo fired its last 4 forward torpedoes at a large stationary cargo vessel, lowering its boats to investigate the unfolding scene. All 4 torpedoes ran beneath the target without effect. Returning to Manila Bay on December 30, the crew faced demoralization after expending all 24 torpedoes without sinking a single enemy vessel. Commander Jacobs submitted a detailed after-action report, emphasizing that the torpedoes were consistently running deeper than their set depths and rendering them ineffective against intended targets. These early experiences revealed a stark contrast. Japanese torpedo technology was extraordinarily effective, while American submariners confronted a persistent and baffling technical failure in their own weapons. The initial underestimation of enemy capabilities, combined with flawed domestic ordnance, would shape the submarine war in the Pacific and exact a heavy toll on Allied naval operations before systemic solutions were implemented. Washington's Bureau of Ordnance, the office charged with designing and manufacturing torpedoes, showed little patience for criticism coming from the Pacific. Reports from submarine commanders describing repeated weapon failures were brushed aside, often with thinly veiled disdain. According to Bureau officials, the fault lay not in the weapon but in the men who used it. Submarine skippers, they argued, misunderstood torpedo upkeep. Crews failed to follow proper firing procedures. Commanding officers approached their targets incorrectly. From the Bureau's perspective, the Mark 14 torpedo represented the pinnacle of American naval engineering. It had undergone extensive testing, at least on paper, and was considered one of the most advanced weapons in the U.S. inventory. Any malfunction, the Bureau insisted, could only be the result of human error rather than flaws in design or construction. This institutional refusal to accept responsibility hardened into policy and remained largely unchanged for almost 2 years. During that time, American submarines launched thousands of torpedoes that failed to perform as intended. Japanese cargo ships absorbed direct hits, only to continue their voyages with unexploded American weapons embedded uselessly in their hulls. Meanwhile, Japanese naval intelligence quietly assembled a detailed picture of what was happening beneath the waves. By monitoring U.S. submarine radio transmissions, exploiting weaknesses in American encryption, and questioning survivors from lost submarines, Japanese analysts compiled extensive documentation of torpedo malfunctions. By early 1942, these findings had reached the Imperial Naval General Staff in Tokyo. The intelligence officers reviewing the data reached conclusions that were accurate in observation but disastrously flawed in interpretation. They concluded that American torpedoes were crude, unreliable devices riddled with fundamental engineering problems. U.S. submarine crews, they believed, lacked proper training, discipline, and the aggressive mindset required for effective undersea warfare. Worse still, they judged American industry itself to be overrated, capable of producing weapons that looked impressive on paper but failed under combat conditions. This assessment, though grounded in real battlefield evidence, misread the underlying reality. It would later stand as one of the most costly intelligence miscalculations of the war. Throughout 1942, the same grim pattern played out again and again across the Pacific Ocean. American submarines shadowed Japanese vessels for hours or days, maneuvered into ideal firing positions, and launched torpedoes that by all logic should have guaranteed destruction. Instead, the results were often nothing at all. The numbers told a sobering story. During 1942 alone, U.S. submarines in the Pacific fired 1,442 torpedoes at enemy ships. Commanders reported the sinking of 211 vessels, claiming nearly 1.3 million tons destroyed. After the war, a detailed comparison with Japanese shipping records by the Joint Army-Navy Assessment Committee revealed the truth. Only 109 ships had actually been sunk, totaling just over 41,000 tons, less than 3% of the claimed tonnage. Submarine patrol reports piled up, filled with detailed descriptions of torpedoes that ran deeper than their set depths, detonated prematurely without damaging their targets, or struck ships squarely and failed to explode at all. Japanese merchant captains began submitting their own reports describing unexploded torpedoes lodged in their hulls as their ships limped back to port. Once docked, Japanese ordnance specialists carefully removed these intact weapons. They studied them closely, not with alarm but with growing confidence. Each recovered torpedo reinforced a dangerous assumption within Japanese naval planning circles. The American submarine threat was exaggerated and manageable. As a result, Japan continued to operate much of its merchant fleet with minimal escort. Convoy systems remained weak, and scarce resources were directed elsewhere. Strategic decisions followed from this belief. Instead of investing heavily in escort vessels, sonar and radar development, or specialized anti-submarine training, Japan prioritized battleships and aircraft carriers in preparation for the decisive fleet engagement its naval doctrine predicted. Anti-submarine warfare was treated as a secondary concern. This false sense of security endured well into late 1943. By the time Japanese leadership recognized the true scale of the submarine threat, it was too late. The merchant fleet, the lifeline of Japan's war economy, was already fatally exposed. The reality, obscured by early American failures, was far more complex and far more dangerous for Japan than its intelligence services understood. At the heart of the problem was the Mark 14 torpedo itself. Designed during the depths of the Great Depression, the weapon was developed under severe budget constraints that sharply limited realistic testing. As a result, it entered service with not one but three major defects, each masking the others and making diagnosis extraordinarily difficult. To understand how these flaws were eventually uncovered and corrected, it is necessary to look back at how the torpedo was conceived and brought into service. Development of the Mark 14 began in 1931 as a replacement for the aging Mark 10 torpedo, a World War I-era design still carried by older S-class submarines. The new weapon was intended for the next generation of fleet submarines boats such as Gato, Wahoo, and Tang, which were expected to form the core of America's undersea force. The design goals were ambitious. The torpedo would measure over 20 feet in length, weigh roughly 3,000 pounds, and carry a powerful 643-pound Torpex warhead. It was expected to achieve speeds of 46 knots at shorter ranges or operate at lower speeds for nearly double the distance. A gyroscopic guidance system would keep it on course, while a hydrostatic mechanism controlled its running depth. Most revolutionary of all was its detonator, the Mark 6 exploder. This magnetic influence device was designed to sense a ship's magnetic field and trigger the warhead beneath the keel rather than on contact. In theory, such an explosion would break a ship's structural spine, guaranteeing catastrophic damage and rapid sinking. On paper, the Mark 14 promised to revolutionize submarine warfare. In practice, its untested assumptions would cripple the U.S. submarine campaign until hard-earned experience, stubborn field commanders, and mounting evidence finally forced the truth into the open. The Mark 6 magnetic exploder was considered a technological breakthrough at the time of its introduction. Unlike traditional contact detonators that required a direct strike against a ship's hull, this device was designed to sense disturbances in the Earth's magnetic field. Large steel vessels naturally altered the surrounding magnetic environment as they passed overhead. When the Mark 6 detected a magnetic fluctuation strong enough to cross its preset threshold, it triggered the torpedo's warhead automatically. This allowed the explosion to occur beneath the ship, where structural damage would be far more devastating than a surface impact. The idea itself was not entirely new. German engineers had experimented with magnetic detonation during the First World War, though results were inconsistent. British naval forces later adopted similar systems with limited but measurable success. What set the American Mark 6 apart was ambition. It was engineered to be more sensitive, more precise, and more technologically advanced than any magnetic exploder that had come before it. The true weakness of the system, however, lay not in its theory, but in how it was tested. In 1931, a single Mark 14 torpedo carried a price tag exceeding $10,000, an enormous sum at the time, equivalent to roughly $200,000 today. The United States was deep in the grip of the Great Depression. Military budgets were aggressively cut, and Congress scrutinized every dollar spent by the Navy. Under such conditions, deliberately destroying expensive torpedoes during live fire trials was seen as wasteful and politically risky. To avoid these costs, the Navy relied almost entirely on non-combat testing. Instead of live warheads, torpedoes were fitted with so-called exercise heads. These dummy warheads were filled with combinations of air and water to approximate the total weight of a real explosive charge. After being fired during test runs, the torpedoes could be retrieved, inspected, and reused. Engineers used these exercises to evaluate depth control systems, steering gyroscopes, and general mechanical reliability. On paper, this approach appeared efficient and economical. In reality, it concealed critical flaws. While the exercise head matched the overall mass of the combat warhead, it did not replicate how that weight was distributed. The real warhead contained 643 pounds of high explosive packed primarily into the forward section of the torpedo. By contrast, the exercise head spread water evenly throughout the compartment. This seemingly minor difference altered the torpedo's balance and behavior in the water, changing its trim and hydrodynamic performance in ways that never became apparent during peacetime trials. Even more troubling, the Navy never conducted full-scale live tests against real ships. The Mark VI exploder was treated as a highly classified device to the point that submarine commanders were not permitted to inspect it or even learn its operating principles. Confidence in the system rested almost entirely on theoretical calculations, controlled laboratory experiments, and test firings that failed to simulate actual combat conditions. The first major consequence of this flawed testing regime appeared in depth control. In combat, Mark XIV torpedoes consistently traveled far deeper than their selected settings, typically by 10 to 11 feet. This problem traced back to changes made late in development. Engineers increased the explosive charge by an additional 80 pounds to improve destructive power, but neglected to recalibrate the hydrostatic depth sensor accordingly. Compounding the issue, the sensor itself was mounted in a poor location along the torpedo's hull, where water flow created unpredictable pressure effects. As the torpedo accelerated through the water, fluid moving rapidly across the sensor produced a localized drop in pressure, a direct application of Bernoulli's principle, the same physical phenomenon that generates lift on aircraft wings. The depth control system interpreted this pressure reduction as an indication that the torpedo was running too close to the surface. In response, it adjusted the control surfaces to force the weapon deeper. The faster the torpedo traveled, the stronger this effect became. The result was universal and catastrophic. Every Mark XIV torpedo fired in combat during 1941 and 1942 ran well below its intended depth. Weapons set to cruise at 10 feet, ideal for striking ships near the waterline, were instead passing 20 to 25 feet beneath their targets. Rather than detonating, they slipped harmlessly under enemy hulls. This defect proved exceptionally difficult to diagnose. Static laboratory tests, which involved suspending torpedoes in still water, showed no abnormal behavior because there was no water movement to trigger pressure changes. Dynamic trials using exercise heads appeared to confirm correct depth performance, but the depth recording instruments suffered from the same flawed sensor placement as the torpedoes themselves. As a result, the data consistently reported correct depths that were, in reality, wrong. The flaw was real, systematic, and present in every weapon deployed, but the Navy's testing methods were incapable of revealing it. On its own, this depth control failure would have severely undermined submarine operations. Yet its effects were initially obscured by an even more elusive problem: the unreliable behavior of the Mark VI magnetic exploder itself. The Mark VI torpedo was engineered to detonate when it sensed the magnetic field of a ship's steel hull above it. Conceptually, this was an elegant solution. The torpedo would pass beneath its target and explode under the keel, where the resulting shockwave and gas bubble could inflict maximum structural damage, potentially breaking the ship's spine. However, in practice, the weapon proved highly unreliable. The intensity and orientation of the Earth's magnetic field are not uniform. They fluctuate with latitude, local geological features, and other environmental factors. The Mark VI had been calibrated and tested near the Naval Torpedo Station in Newport, Rhode Island, where the local magnetic conditions suited its design perfectly. Yet, when deployed in the Pacific Theater around Java, the Philippines, the Guadalcanal area, and the waters surrounding Japan, the local magnetic conditions differed dramatically. The torpedoes set up for Newport frequently failed in real combat situations. Some detonations occurred prematurely, sometimes 50 to 100 yards before reaching the intended target. The magnetic exploder was triggered too early by the ship's magnetic signature, causing explosions that caused almost no damage, merely alerting the enemy and allowing them to evade. Conversely, other torpedoes passed under the target without detonating at all, as the local magnetic variations were insufficient to activate the device. Submarine commanders, observing through their periscopes, witnessed seemingly perfect shots result in useless detonations, leading to mounting frustration. Repeated after-action reports documented these failures, often including recommendations to disable the magnetic feature entirely. Despite these reports, the Bureau of Ordnance consistently attributed the malfunctions to errors in maintenance, incorrect calibration, or deviations from standard operating procedures. A complicating factor was that multiple defects interacted in ways that obscured their origins. Torpedoes running too deep failed to trigger the magnetic detonator because they passed beneath the area where the magnetic effect could be detected. Adjusting depth was assumed to fix the magnetic problem, yet even after depth calibration was corrected around mid-1942, the Mark VI's magnetic function continued to misfire. This revealed a third critical flaw, the contact exploder. The Mark VI combined both magnetic and contact detonation mechanisms into a single system. If the magnetic component failed, the contact system was supposed to activate upon impact with the ship's hull. This mechanism relied on a firing pin design that had performed reliably in older, slower torpedoes such as the Mark X, which reached 36 knots. The Mark XIV, which replaced the Mark X, operated at a significantly higher speed of 46 knots, approximately 28% faster, but no testing had been done to confirm that the contact system could survive such high-velocity impacts. When a Mark XIV torpedo struck a steel hull at full speed, the deceleration was sudden and violent. The firing pin, relatively heavy and restrained by a spring calibrated to avoid accidental detonation during handling, often became jammed in its housing before it could activate the detonator. In practical terms, direct hits at a 90-degree angle, precisely the type of shot emphasized in submarine training, were the most likely to fail. Only glancing or oblique impacts, which slowed the deceleration, allowed the firing pin to function as intended. A similar issue had been identified and resolved in earlier torpedo designs back in 1922 by using a lighter pin and stiffer spring. That knowledge was neglected when the Mark VI was developed, and the contact mechanism was simply carried over without validation for the higher speed of the Mark XIV. The consequences were glaring. Japanese vessels frequently returned to port with American torpedo dents, and sometimes even with unexploded torpedoes lodged in their hulls, a stark humiliation for USS. Submarine crews who had executed seemingly perfect attacks. The combination of the magnetic and contact detonator failures resulted in catastrophic operational inefficiencies, contributing to massive missed opportunities and the loss of American lives during 1942 and the early months of 1943. During World War II, American submarine commanders frequently faced excruciating frustration in combat. They would shadow enemy vessels for prolonged periods, sometimes spanning hours or even days, carefully maneuvering into positions ideal for attack, all while under constant threat from Japanese anti-submarine defenses. Once in position, they launched torpedo spreads intended to guarantee hits, only to witness repeated failures, torpedoes that misfired, detonated too early, or passed harmlessly through the target. The psychological toll on crews was intense. Sailors who had spent years training to operate submarines, aware that their service carried the highest casualty rate among U.S. Tabor combat forces, and who executed attacks with precision, were confronted with the demoralizing reality that their most critical weapon was often unreliable. A stark example occurred in January 1942 when Lieutenant Commander Frederick Warder, commanding the submarine Seawolf, engaged an 8,000-ton Japanese transport anchored in Tolomo Bay, Philippines. The target was stationary, unprotected, and in conditions that should have ensured success. Warder fired 4 Mark XIV torpedoes at close range, only to hear dull clangs as each struck the hull without detonating. The transport, alerted but unharmed, maneuvered away and signaled for air support. Warder then switched to the older Mark X torpedoes, outdated weapons from World War I that lacked the advanced mechanisms of the Mark XIV, but these functioned correctly. One exploded against the ship's stern, and another hit midship, breaking the vessel's keel. The transport sank within minutes. In his report, Warder explicitly recommended withdrawing the Mark XIV torpedo from service. The Bureau of Ordnance ignored the warning, dismissing the incident as a result of Warder's supposed poor torpedo maintenance and insufficient training. A similar incident occurred in April 1942 with Lieutenant Commander Eugene Fluckey of the submarine Tambor. Fluckey launched 8 torpedoes at a Japanese destroyer from a distance of 800 yards. Each torpedo struck the target's hull but failed to explode. The destroyer, now fully aware of Tambor's presence, retaliated with depth charges that rattled the submarine systems and caused leaks throughout the vessel. The boat barely escaped, surfacing later under cover of darkness to ventilate and perform emergency repairs. Fluckey recovered 8 torpedoes from the water, all unfired, carefully documented their condition, and sent a detailed report to Pearl Harbor. Yet the Bureau of Ordnance accused him of mishandling the torpedoes and failing to maintain them properly instead of addressing the design flaws. Japanese intelligence monitored these communications and partial decrypts, noting that American submarine commanders frequently blamed their own weapons for failed attacks. This misperception reinforced Japanese assumptions of technological superiority and contributed to their underestimation of the submarine threat. Consequently, Japanese anti-submarine tactics remained oriented toward defending major fleet units rather than merchant shipping. Patrol craft and destroyer escorts, designed mainly for surface engagements, lacked effective sonar and depth charge capabilities, and the Navy's doctrine provided minimal guidance for anti-submarine operations. Moreover, Japanese shipbuilding priorities focused on battleships and carriers in preparation for decisive fleet battles rather than on modest convoy escorts. The torpedo crisis reached a tipping point in mid-1943. On June 10, 1943, Commander Roy Benson, leading the submarine Trigger, engaged the Japanese fleet carrier Ho, a key asset in the Japanese naval air strategy. Benson maneuvered into an optimal firing position 1,200 yards from the target and launched 6 torpedoes in a precisely calculated spread. Despite this near-perfect approach, the attack produced mixed results. 2 torpedoes missed due to evasive maneuvers, 1 detonated prematurely before reaching the carrier, another struck but failed to explode, and only 2 functioned correctly, causing moderate damage that slowed the ship and ignited fires. POWES, supported by destroyer escorts, survived and returned for repairs, rejoining service within 6 weeks. It would later participate in the Battle of the Philippine Sea in June 1944, before finally being sunk by the submarine Archerfish. The June 1943 failure illustrates the strategic consequences of the faulty Mark XIV torpedo. Had it been destroyed at the time of Benson's attack, her aircraft would not have been available for operations that inflicted casualties on American forces. Every torpedo that failed not only compromised individual engagements, but had broader implications for the Pacific War, delaying the attrition of Japanese naval power and extending the conflict. The event that finally removed any remaining doubt and compelled decisive action occurred in the summer of 1943. By that point, complaints about malfunctioning torpedoes had been circulating for nearly 2 years, but none had delivered undeniable proof until this patrol. On July 24, 1943, Lieutenant Commander Lawrence Daspit was leading the American submarine Tenosa on her second combat mission. While operating south of Truk, Daspit detected a solitary Japanese vessel of exceptional size, the 19,250-ton whale factory ship Tonan Maru No. 3. The ship was sailing without escort, isolated in open water. For a submarine commander, it was the ideal target. The vessel was massive, slow-moving, unarmed, and highly valuable. Even more importantly, it carried whale oil, an essential resource for Japan's wartime economy. Whale oil was a critical ingredient in the manufacture of nitroglycerin used in explosives, as well as in food production and multiple industrial applications. Destroying the ship would not only cause immediate loss but also disrupt supply chains vital to Japanese industry. Daspit maneuvered detonator into firing position at a distance of approximately 4,000 yards and launched 4 torpedoes. Through the periscope, he clearly observed 2 successful impacts that abruptly halted the ship. Acting quickly, he fired 2 additional torpedoes. Both struck the target as well. Under normal circumstances, 6 confirmed torpedo hits would have been more than sufficient to sink any merchant vessel afloat. Yet Tona Maru No. 3 refused to go down. She remained motionless, crippled but still floating. No enemy escorts or anti-submarine forces were present, giving Daspit time to reassess. Confident in his positioning, he moved detonator into what submarine doctrine defined as the perfect firing setup, just 875 yards away, positioned directly abeam of the target. At this distance and angle, a miss was virtually impossible, and every torpedo would strike at an ideal 90-degree angle, precisely the scenario American submariners were trained to achieve. Daspit fired 9 more torpedoes in succession. Despite incoming machine gun fire from the Japanese ship, he remained at periscope depth and carefully observed each torpedo's approach. One after another, all 9 struck the stationary vessel squarely at the optimal angle. None detonated. Inside detonator, the crew could hear the muted metallic thumps as torpedoes slammed into the hull of the target without exploding. 15 torpedoes had been fired under near-perfect combat conditions. Everyone functioned flawlessly except in the single respect that mattered most. Not a single warhead exploded. Convinced that the failure pointed to a manufacturing defect rather than chance or crew error, Daspit deliberately withheld his final torpedo. He intended it to be examined by technical specialists upon return to Pearl Harbor. With the risk of Japanese aircraft increasing, detonator withdrew from the area. Rear Admiral Charles Lockwood, who had assumed command of submarines Pacific Fleet in January 1943, immediately recognized the significance of Daspit's report. This was not anecdote or speculation. It was a controlled, repeatable experiment conducted in combat, documented with photographs and meticulous observations. Lockwood was no stranger to submarines. He had commanded them during the interwar years and understood both their strengths and vulnerabilities. For 2 years, he had listened as his captains described torpedoes running too deep, exploding prematurely, or striking targets without detonation. Throughout that period, the Bureau of Ordnance had consistently dismissed these reports, attributing failures to crew mistakes, poor upkeep, or improper firing techniques. Lockwood had also witnessed the toll these failures took on morale. Submarine crews were executing textbook attacks under extreme danger, only to see their weapons betray them. Intelligence reports further suggested that Japanese ships were reaching port with unexploded American torpedoes embedded in their hulls. Now, with Daspit's patrol report in hand, Lockwood had undeniable evidence. He concluded that the contact exploder, the device designed to trigger detonation upon impact, was fundamentally flawed. He ordered immediate testing. Under Lockwood's direction, a test facility was constructed using steel plates positioned at varying angles. Dummy torpedo warheads were dropped from a pier crane to simulate real impact conditions. The results were conclusive and alarming. At high impact speeds, particularly during direct 90-degree strikes, the firing pin mechanism jammed. Sudden deceleration caused the heavy steel firing pin to bind before it could strike the detonator. Ironically, the most precise shots, the very ones submariners were trained to deliver, were the most likely to fail. Perfect aim produced the highest deceleration forces, rendering the exploder useless. The solution emerged from an unexpected wartime observation. During the attack on Pearl Harbor, American anti-aircraft fire had downed several Japanese aircraft. Engineers examining the wreckage noticed that the propeller blades were not steel, as used in American designs, but made from a lightweight aluminum alloy. The material was strong enough for aviation use while being significantly lighter. This discovery sparked a crucial insight. If the torpedo's firing pin were made from aluminum instead of steel, it would possess less inertia and be far less likely to bind during sudden deceleration. Tests validated the theory. By September 1943, nearly 2 years after the attack on Pearl Harbor, modified torpedoes featuring aluminum firing pins and additional improvements began reaching American submarines operating from Pearl Harbor and Fremantle. The impact was immediate and dramatic. What followed was one of the most significant reversals of combat effectiveness in naval history. From December 1941 through August 1943, American submarines had been fighting with a primary weapon system that was barely functional. The Mark 14 torpedo suffered from three independent but overlapping defects. Each concealed the others, making diagnosis slow and resistance to reform easier to maintain. Submarine commanders adapted however they could. They adjusted depth settings to compensate for faulty depth control. Against orders, they disabled magnetic exploders to avoid premature detonations. They avoided ideal firing angles, opting instead for oblique shots that were statistically less likely to trigger the contact exploder's failure. These measures were improvised survival strategies, not solutions. After September 1943, with all three major defects corrected, the Mark 14 finally performed as originally intended. Depth mechanisms operated accurately. Magnetic exploders were permanently abandoned. Contact detonators functioned reliably at all angles and speeds. The commanders who had endured 2 years of combat with defective weapons, who had learned through failure, frustration, and loss, now possessed torpedoes they could trust. The effect on Japanese merchant shipping was swift, overwhelming, and irreversible. During the early years of World War II, specifically through 1942 and the beginning of 1943, Japanese naval strategists had largely underestimated the threat posed by American submarines. They considered the undersea menace manageable and structured their convoy protection accordingly. Priority was given to safeguarding high-value naval assets such as aircraft carriers, battleships, and troop transports, while the merchant fleet responsible for ferrying essential raw materials from occupied territories to Japan and transporting finished military products to distant bases received only minimal escort. Destroyers and patrol vessels were deployed primarily to cover major naval formations rather than to shield commercial shipping. Japanese anti-submarine doctrine focused on protecting strategically significant military targets, assuming that enemy submarines could not inflict decisive damage on maritime logistics. This judgment proved disastrously inaccurate once the United States resolved the persistent reliability issues with its torpedoes. On December 22, 1944, Commander Reuben Whitaker, commanding a U.S. submarine, intercepted a convoy near the Chinese coast. Whitaker skillfully maneuvered into position and launched 6 torpedoes at 3 tankers. Remarkably, every torpedo struck its target. The ships, the 10,000-ton Omarosan Maru, the 9,200-ton Arita Maru, and the 9,200-ton Ottawasan Maru, were transporting vital fuel oil from the Dutch East Indies to Japan. All 3 vessels sank within 20 minutes, resulting in the loss of over 28,000 tons of shipping and hundreds of thousands of gallons of irreplaceable fuel. Even more dramatic accomplishments were achieved by Commander Eugene Fluckey aboard the submarine Barb. During her 11th war patrol in 1945, Barb sank 17 enemy ships totaling more than 96,000 tons, setting a single patrol tonnage record that has never been surpassed. Earlier, on June 23, 1944, off the coast of China near Namuan Harbor, Fluckey executed a concentrated attack on a convoy, sinking 4 ships totaling over 15,000 tons in just 54 minutes. These successes were no coincidence. They reflected highly disciplined tactics, precise execution, and the deployment of torpedoes that now functioned as intended, combined with commanders who had refined their techniques through extensive combat experience. The shift in effectiveness is clearly illustrated by statistics. In 1942, U.S. submarines fired 1,442 torpedoes, claiming 211 ships for roughly 1.3 million tons, but the actual damage amounted to 109 ships for only 41,871 tons. As torpedo reliability improved in 1943, submarines launched 3,937 torpedoes, sinking 284 vessels and totaling 1,349,473 tons. By 1944, with fully operational weapons, 6,922 torpedoes yielded 492 sunken ships totaling 2,388,000 tons. This represents nearly a tenfold increase in effectiveness once mechanical problems were resolved. By the war's end, American submarines had destroyed 1,178 Japanese merchant ships, representing 5,533,491 tons, more than half of all Japanese shipping losses. Additionally, 201 Japanese naval vessels were sunk, including the Shinano, an aircraft carrier displacing 72,000 tons, the largest warship ever destroyed by a submarine. The impact on Japan's wartime economy was profound. As an island nation, Japan's survival depended entirely on maritime supply lines. Raw materials from Southeast Asia, China, and the Dutch East Indies were crucial for industry, while finished military equipment needed to be shipped outward to frontline bases. Fuel imports, especially oil from the Dutch East Indies, were essential for both military operations and civilian needs. By January 1945, the Japanese merchant fleet had been reduced to barely a quarter of its pre-war size. Oil tankers were being sunk faster than they could complete a single voyage, and cargo ships were going down fully loaded. Food imports had dwindled to the point that rationing verged on starvation. The disruption of resources triggered a cascading collapse across the industrial and military sectors. Refineries ceased production without crude oil. Steel mills halted due to shortages of iron ore and coking coal, and aircraft factories stalled because of missing aluminum. Fuel shortages grounded naval and air operations. Ships and aircraft sat idle, and pilot and sailor training programs stalled. The Imperial Japanese Navy, once a dominant maritime force and the third largest navy in the world, became immobilized. Army divisions stationed across China, Southeast Asia, and the Pacific Islands were left vulnerable, deprived of reinforcements and essential supplies. The strategic balance in the Pacific had shifted irreversibly, with undersea warfare by American submarines crippling the lifelines of a nation entirely dependent on sea transport. Supplying the Japanese military became an increasingly impossible task as the war progressed. Ammunition, replacement weapons, medical equipment, and food all had to be transported from the Japanese home islands, yet an ever-growing number of these shipments never reached their destinations. Isolated garrisons were often left to endure months without resupply, as Allied submarines systematically intercepted and sank the freighters that served as their lifeline. Reinforcements meant to replenish battle losses were similarly vulnerable, with troop transports falling victim to torpedo attacks. Despite having conquered large swaths of Asia in defeating Chinese, British, Dutch, and American forces in the early stages of the war, Japan found itself trapped in a slow suffocation, its fortified positions gradually rendered unsustainable because the logistics network sustaining them was being dismantled beneath the surface of the oceans. The Japanese home islands faced a looming famine as essential food imports from Korea, Formosa, and Southeast Asia dwindled. Japan had never been able to produce enough food domestically and relied heavily on these imports to feed its population. By 1945, the supply of these vital goods had been reduced to a mere trickle due to persistent submarine attacks on cargo ships. Residents of Tokyo, Osaka, Kobe, and Nagoya were forced to endure steadily shrinking rice rations, and black markets thrived as civilians scrambled to acquire even minimal provisions at exorbitant costs. The government imposed strict measures to maintain order, but the underlying reality was unavoidable. Without imported food, survival for the population was increasingly impossible. While American strategic bombing of Japanese cities has often dominated historical narratives and popular memory, it was, in fact, secondary to the silent, relentless effectiveness of the submarine campaign in crippling Japan's ability to continue the war. Firebombing campaigns caused massive destruction and terror among civilians, yet the immediate impact on the war economy was limited. Factories simply could not function without essential raw materials such as steel, aluminum, coal, and oil. By the time the atomic bombs were dropped on Hiroshima and Nagasaki on August 6 and 9, 1945, Japan's surrender had a visible justification, but the nation had already been defeated economically and militarily. The foundations of its war effort had been systematically destroyed by the submarine blockade, leaving Japan incapable of sustaining further combat regardless of battlefield events. The story of the Type 93 long-lance torpedo encapsulates the shift in naval fortunes. In 1942 and 1943, this weapon instilled fear in Allied navies and was often cited by Japanese intelligence as evidence of technological superiority. By 1944, however, it had lost much of its significance. Advances in radar warning systems allowed American ships to detect Japanese surface forces in advance and take evasive action before torpedoes could be launched. Damage control procedures had improved, enabling vessels to survive hits that would have sunk them earlier in the war. Tactical formations reduced exposure to torpedo attacks, further diminishing the weapon's impact. Crucially, aggressive American surface forces, supported by overwhelming air superiority, were destroying the very platforms, destroyers and cruisers that launched these torpedoes faster than Japan could replace them. What was once considered a decisive tool of Japanese naval power had become secondary, as these ships were diverted to escort duties protecting the increasingly vulnerable merchant fleet, a task for which they were neither designed nor effective. The transformation of naval power was starkly illustrated during the Battle of the Philippine Sea in June 1944. On June 19, the submarine Kavala, commanded by Herman Kossler, intercepted the Japanese fleet carrier Shukaku as it recovered aircraft following strikes against American forces. Kossler launched 6 torpedoes at a range of approximately 1,200 yards, with 4 successfully detonating the carrier's aviation fuel storage, triggering catastrophic secondary explosions. Shukaku, a veteran of Pearl Harbor, Coral Sea, and Santa Cruz, sank within minutes, taking 1,263 crew members with her. Later that day, the submarine Albacore, under the command of James Blanchard, struck the newly completed carrier Tiho with a single torpedo. Initially perceived as minor damage, Japanese damage control officers attempted to ventilate gasoline fumes using full power systems, inadvertently spreading explosive vapors throughout the ship. 7 hours later, the vessel detonated violently, breaking apart and sinking rapidly with the loss of 1,650 sailors, including the entire staff of Vice Admiral Jizaburo Ozawa. These attacks were not the result of luck but careful planning and precise execution, demonstrating the devastating efficiency of American submarines against targets that Japan could ill afford to lose. The destruction of Shukaku and Taiho alone accounted for roughly 40% of Japan's remaining large carrier force, effectively crippling Japanese naval aviation at a critical moment. By neutralizing both the logistics network and key warships, the Allies ensured that Japan's military capacity was systematically dismantled long before the atomic bombs provided a public justification for surrender. The Battle of the Philippine Sea, often referred to by American aviators as the Great Marianas Turkey Shoot, marked a decisive turning point in the Pacific theater. During this engagement, Japanese carrier-based air forces suffered catastrophic losses, with over 600 aircraft destroyed in a single day, while American forces lost only 29 of their own planes. The battle effectively ended the threat posed by Japanese carriers for the remainder of the war. Prior to the aerial engagements, WWII submarines had already inflicted devastating damage, sinking 2 of Japan's irreplaceable fleet carriers. Japanese naval strategists, relying on outdated assessments that underestimated the submarine threat, had deployed their carriers through waters heavily patrolled by American submarines without adequate anti-submarine protection. This miscalculation resulted in irrecoverable losses. Without carriers to house trained pilots and operational air groups, Japanese naval aviation, once dominant in the Pacific skies of 1942, was rendered largely ineffective by mid-1944. The relentless submarine campaign had delivered blows that sealed Japan's aerial fate. The October 1944 Battle of Leyte Gulf demonstrated the cumulative effects of sustained submarine operations and the dramatic shift in technological and operational advantage. On October 23, as Admiral Takeo Kurida's center force advanced toward the Philippines via the narrow Palawan Passage en route to Leyte Gulf, American submarines Dart and Dace lay in wait along the predicted route. This deployment was informed by superior intelligence from U.S. code-breaking efforts, showcasing the integration of signals intelligence into tactical operations which had become a hallmark of American submarine warfare. By 532 hours, Commander David McClintock, commanding the submarine Dart, detected the Japanese formation on radar at a distance of 30,000 yards. He maneuvered to an optimal attack position, shadowing the enemy column for 4 hours while relaying contact reports that enabled Commander Bladen Claggett on Dace to align for a coordinated strike. At 927, Dart launched 6 torpedoes at the heavy cruiser Otago, Kurita's flagship. 4 torpedoes struck, rupturing the hull below the waterline, cutting off electrical power and flooding engineering compartments. The vessel sank rapidly, taking 360 of her 800-man crew with her, while survivors, including Admiral Kurita and his staff, abandoned ship into the oil-slicked waters. Immediately afterward, Dart redirected its attack to the heavy cruiser Takao, firing 4 torpedoes, all of which struck. Although Takao did not sink outright thanks to damage control efforts, she was gravely crippled and forced to withdraw under the escort of 2 destroyers, ultimately spending the remainder of the war under repair in Singapore, never returning to combat. Meanwhile, Dace, attacking from the opposite side of the formation, targeted the heavy cruiser Maya, firing 4 torpedoes at 956. Multiple hits fractured the keel and detonated onboard magazines. The ship broke apart and sank within 8 minutes, claiming 769 of her 1,000 crew members. In under half an hour, these 2 submarines had destroyed 2 heavy cruisers, severely damaged a third, and left Admiral Kurita without his flagship, operational staff, or reliable communications at the onset of the largest naval engagement in history. Forced to transfer his command to the battleship Yamato, Kurita lost essential equipment, charts, and personnel, delaying critical decisions. His subsequent conduct at Leyte Gulf, marked by hesitation and ultimately withdrawal despite the proximity of vulnerable American landing forces, was likely influenced by the disruption caused by the submarine attacks. While it is impossible to determine with certainty how Kurita might have acted with his original command intact aboard Otago, the loss of command infrastructure undeniably contributed to his caution. The broader consequences of Leyte Gulf were decisive. The Imperial Japanese Navy was effectively neutralized as a fighting force. In the course of this engagement, Japan lost 1 fleet carrier, 3 light carriers, 3 battleships, 6 heavy cruisers, 4 light cruisers, and 11 destroyers. The combination of American submarine operations, air superiority, and intelligence-driven coordination had fundamentally altered the balance of power in the Pacific, leaving Japan's once formidable naval forces incapable of challenging U.S. dominance for the remainder of the war. By early 1945, the Japanese fleet, including the mighty battleship Yamato, found itself effectively immobilized within home waters. Submarines had destroyed tankers faster than Japan could replace them, creating a crippling fuel shortage. When Yamato embarked in April 1945 on a one-way mission aimed at striking American forces at Okinawa, she carried only enough fuel for a single voyage. She never reached her target. American carrier-based aircraft sank her, taking 2,498 of the 3,332 sailors aboard. The remaining Japanese carriers, immobilized by a lack of fuel, could neither train replacement pilots nor conduct offensive operations. Their air groups were largely expended in kamikaze attacks, leaving the fleet ineffective. Japan's long-prepared doctrine of decisive fleet engagements crafted over 4 decades was rendered irrelevant. The defeat did not stem from poor tactics or lack of courage, but from the systematic destruction of the logistics network that sustained the Navy. American submarines, underestimated by Japanese intelligence, had dismantled Japan's ability to supply its fleet. By this stage, shipping losses had escalated to catastrophic levels, making it economically impossible for Japan to continue the war. American submarines were highly effective due to a combination of reliable torpedoes, intelligence gleaned from code-breaking, and aggressive commanders trained in wartime operations. Their attacks decimated Japanese merchant shipping at a pace far beyond Japan's capacity to replace it. In January 1945 alone, U.S. submarines sank 252,000 tons of Japanese merchant vessels. February saw 182,000 tons lost, March 200. Each month, the tonnage destroyed exceeded Japan's entire domestic shipbuilding output multiple times. Every loss was compounded. Not only cargo but crews, shipyard output, and Japan's strategic mobility vanished with each sinking. Japanese shipyards, operating at maximum efficiency, could produce roughly 300,000 tons of merchant shipping annually, assuming they had sufficient steel, labor, and electricity, all of which were increasingly scarce. Yet, American submarines were sinking more than 3 times that tonnage each month. The arithmetic was inexorable. Japan's merchant fleet was steadily approaching extinction, independent of naval or army operations on the battlefield. By August 1945, very few Japanese merchant vessels remained, and those that survived were confined to port, unable to risk the waters patrolled relentlessly by American submarines. The human toll was equally severe. Japanese merchant sailors, civilians tasked with transporting vital supplies, suffered devastating casualties. Many were trapped as torpedoes ruptured hulls, drowned in oil-slicked seas, burned when tankers exploded, or perished after drifting for days or weeks in lifeboats with little hope of rescue. The Imperial Japanese Navy provided no systematic merchant marine rescue service, viewing these sailors as expendable rather than critical national resources. In contrast, American submarine commanders, while operating under orders for unrestricted warfare, often surfaced to offer survivors water, food, and directions to land. Cultural indoctrination led some Japanese sailors to refuse such assistance, believing enemy aid dishonorable or dangerous. This catastrophic outcome was compounded by critical intelligence failures. In 1942, Japanese naval intelligence observed widespread American torpedo malfunctions and erroneously concluded that U.S. weapons were fundamentally unreliable. Consequently, Japan prioritized traditional doctrines, emphasizing decisive battles over convoy protection and anti-submarine measures. Even after American engineers corrected these deficiencies, Japanese intelligence was slow to recognize the improvements and even slower to adapt operational strategies accordingly. By the time Japanese planners understood the full scope of the submarine threat, it was far too late. The merchant fleet had been destroyed, shipping losses had crippled the economy, and Japan's ability to wage war had collapsed. Victory in the Pacific, therefore, was determined not by dramatic carrier engagements like Midway or the Philippine Sea battles that captured public imagination, but by the relentless attrition imposed by American submarines. The same weapon Japanese analysts had once mocked became the decisive instrument of defeat, demonstrating that underestimating an enemy's capacity to adapt and innovate can be fatal. The submarine campaign epitomized industrial warfare at its most merciless. Through persistent application of resources, engineering solutions, and tactical skill, the U.S. Navy imposed a strategic suffocation on Japan. Japan's defeat was not a consequence of battlefield inferiority alone. It was a product of industrial arithmetic and strategic foresight. Submarines, initially dismissed as flawed and ineffectual, sank more shipping than all other American forces combined, dismantling the maritime infrastructure upon which an island nation's survival depended. The lesson was clear. Wars are won as much by the management of logistics, the ability to recover from failures, and the mobilization of industrial capacity as they are by tactical brilliance. Japanese intelligence's failure to anticipate American adaptation and engineering acumen transformed what seemed like temporary technological setbacks into irreversible national catastrophe, ensuring that the empire's fate was sealed long before the final surrender.